1 second. So at the last time we are stopped at the energy equation at heat form in absolute motion. So how to... So do you see it?
Yes.
So at last time we are find the energy equation at heat form in absolute motion. It's only brief refresh information for you. So, and the main conclusion from this equation was, we received two conclusions. First moment, what supplying external heat and supplying mechanical work, and at the process are using for changing enthalpy and changing of kinetic energy. It's the first conclusion. But for the turbomachinery, one second. For turbomachinery, we have no external heat, and that's why for turbomachinery, this conclusion sound like what all supplying mechanical energy to change an enthalpy and kinetic energy of the flow. It's the first moment, first conclusion. And the second conclusion, what the total temperature change only in the case then you are supplying mechanical energy and supplying external heat. At the case of turbomachinery, we have no external heat. That's why in the turbomachinery, total pressure change only in the case that you are supplying mechanical energy. And that's why total temperature change only in the case, change only in the rotor wheels. And I pay your attention what the total temperature are not depend from the losses. And that's why in non-moving guide vanes, nozzle guide vanes, tubes, nozzles, what else, intakes, some channels, it's not change. The total temperature will be constant in all non-movable channels. So let's discuss the last energy equation. It will be inner energy equation in heat form in relative motion. These equations are received like in the previous case, like in the energy equation at heat form in relative motion. But, in absolute motion. But we will take the energy equation in mechanical form in relative motion, the differential shape of this equation. We are a little bit modify it. We are change density to specific volume, and we are says what in ideal case, the process in the turbomachinery are adiabatic. We are not supplying any heat, but in reality, these processes are not adiabatic, and we are supplying some internal heat. And source of the internal heat, it's the losses, because finally all friction, all separation are converted to the heat, and these heat are supplied to the flow inside the turbomachine. So it's the first idea. After that, we are write the first law of thermodynamic, which says for us what all external and internal heat are used to change internal energy of the flow and creating mechanical work. So from this equation we are extract external heat, And we are said what all external heat, the source of external heat, it's the losses, and that's why we are said what all losses are equal to the external heat, and we are extract this relationship from the equation of the first law of thermodynamics and put it inside the energy equation in mechanical form in relative motion. And finally, we are receive this equation, and we are remember what first two term it's the enthalpy. And after all conversation, we are receive this equation, which are called energy equation at heat form in relative motion. I hope you are previously received this equation during studying of the course of gas dynamic or maybe thermodynamic course, but very often the professors who read in a lecture about the thermodynamic and gas dynamic miss this equation because maybe we are not think what it's very important equation, but for turbomachinery this equation are important. And that's why maybe you are not studied this equation in the gas dynamic courses previously. So, of course, for us it's much interesting to receive the conclusions deal with the working process of the turbomachinery. So, first of all, one second. Let's try to carefully read this equation, and first of all, let's try to understand the physical mention which are lays inside this equation. So, first conclusion, let's hide this part of equation. Let's hide it. And let's simply read this equation. What we are receive? The work of inertia force and supplying supplying external heat in the process are used to the change of enthalpy of the flow and change the kinetic energy of the flow in the relative motion. It's the first conclusion. Of course, it's the common conclusion. If we will speak about the turbomachinery, in the turbomachinery we have no external heat. We are not supplying external heat. That's why for the turbomachinery we could to say what the work of inertia forces in the rotor wheels of the turbomachinery are used to the change of enthalpy and change of kinetic energy of the flow in relative motion. It's the first conclusion. The second conclusion, let's hide this part of equation. Sorry. Let's hide this part of equation. And let's simply read this equation. What we could to say? The total temperature of the flow stagnating in relative motion TW with the star will change only in the case of the supplying of external heat and moving in the field of action of inertial forces. By other word, TW with the star depend only from external heat, but in the turbomachinery we have no it. That's why in the turbomachinery TW with the star do not depend from the heat and action of inertia force. By other words, if in the turbomachinery you are not change the diameter, it's mean what you are not change the circumferential velocity, it's mean what the TW will be constant. So in any case, these relationships are widely used during calculation process of the stage calculation for how to say, one second, for the recalculating of parameters from the section in the inlet of the rotor wheel to the section at the outlet rotor wheel. This equation connect to cross section during calculation process of the turbomachinery. So the next conclusion. Let's set the new term. The temperature of the flow stagnated in relative in the rotating wheel. So you will T omega this the star. You will see how to receive this temperature, and if you are put this new value inside the energy equation heat form in relative motion, you are receive such equation. It's mean what T omega with the star will be changed only in the case then you are supplying external heat. Turbomachinery, we are not supplying external heat. That's why for the turbomachinery in the rotor wheel, the value of T omega with the star will be constant. And it's really very convenient. It's really very good to have a value which doesn't change during process. It's like conservation of the energy, and it's really very useful for the calculation of the parameters between the inlet section and outlet section of the rotor wheel. And the last conclusion. So maybe I will erase it. So let's take this part of equation and write it to for the compressors. So, and let's take the enthalpy value to the left part of equation, and all other terms we will move to the right part of equation. And of course we are, remember what we have no external heat in the turbomachinery, that's why we are remove this term. And finally we are receive this this formula which explain why static temperature are changed in the stage of the compressor. Because sometimes it's not clear, but sometimes during exam I ask, please explain to me how the static temperature are changed along the stage of the compressor stage. And this equation explain why and how the static temperature are changed along the stage. So and how the static temperature are changed along the compressor stage. Very simple. We need to read this equation. The changing of the static temperature of the compressor stage is due to because we have acting of inertia forces and breaking the flow in relative motion. If we will speak about axial stage, this is for centrifugal compressor or for common compressor. If we will speak about the axial compressor, this term will be leads to zero, and that's why for the axial compressor stage the static temperature will be increased because we are breaking the flow in relative motion. If we will return back, we will find, sorry, here must be few words. So if we are returning back, we will find what the reason of increasing of static temperature, the same like the reason of increasing of the static pressure, So that's all about the energy equation. Do you have any questions here? No? Okay.
No questions.
Perfect. And the last equation for today, it will be one before the last equation at this chapter. Momentum equation. From the theoretical mechanic, you know the momentum equation, momentum conservation law. And you could do refresh the information from theoretical mechanic course. And it sounds like impulse of external and internal forces acting on the body with the mass m are equal to the change momentum of the mass. And this is formula from the theoretical mechanic courses, which are explain this law. So let's apply this law for the flow inside the turbomachinery. We are start from the axial compressor stage. So let's imagine what we have axial compressor stage. It's the rotor wheel, but it's not very important at this case. But okay, let it will be a rotor wheel. And let's imagine what we know all information about the flow in the inlet of the rotor wheel. So we know everything about the flow in the inlet. Pressure, density, velocity, flow angles, everything. And the same, we know everything about the flow at the outlet of the blade roll. So let's take one random flow channel and let's draw the random shape line 1, 2 in the random place of channel. So it's really will be a random shape line. It could be straight line, it could be arc, it could be sinus line. It's not important at this case. And this line could be located in the place of the flow channel. So, and we draw the same line in the same place of the nearest channel. So, what it means? We have the line 1, 2, and at the same time of the near channel, we draw the same line at the same position and the same shape. The distance between the line 1, okay, maybe it will be 3, I don't know how to say it on English, 1, 3 and 2, 4 equal to the pitch between the blades. So let's investigate the flow inside the figure 1, 2, 4, 3. So we will investigate the flow inside this figure, and we are not taking account blades because we are investigating only flow. So we are extracting this volume, and of course we will need to replace the action of environment by action of the forces to keep the flow at the same conditions. What kind of forces are impact to this volume? So what volume I mean, it's this volume. What forces are impact to this volume. First of all, at the inlet of the volume, we have pressure P1. We know it because we know everything about the inlet section. At the outlet section, we have pressure P2, and we know this pressure too. At the line 1, 2 are acting pressure P1, 2. 1 second, 3, 4. And to the line 3, 4 are acting force pressure P3, 4. But here we have one interesting moment. We have the same line which comes from the section of the two channels with the same flow. We are think what the flow inside the first channel and the flow inside the second channel are identical. And that's why this line and this line have the same pressure. By other words, pressure P12 and pressure P34 are equal, but these pressure are direct to the opposite directions. That's why the resulting force of acting pressure P12 and P34 will be equal to 0. That's why we are not taking in account these two pressures. So, and we are receive at this moment what only inlet and outlet pressure are acting to this volume. And of course, from the blades, we have acting of the some forces. So, by other words, the blades acting to this volume which we are investigating by force R, and this force could be split to two projections. Circumferential projection RU and axial projection RA. And the same force based to the third law of the Newton are acting to the blade. So it's mean what to the blades to the blade are acting the same force P, and we could to split it to two projection, PU circumferential projection and PA it's the axial projection. So, but for us it's important what for our volume we have influence of the two pressures, inlet and outlet, and the influence of the force which acting to the flow from the. So, and let's apply this law, momentum conservation law, to the flow in the compressor. We will apply it along the coordinate axis. First, we are write this law along the axial direction, and at the slide it's the vertical direction. And finally, we are receive such equation which are connect force RA and flow parameters. But based to the third law of the Newton, we could to say what force PA, which acting to the blades from the flow, are equal to the force RA with the sign of minus. And the same we could to write convert to the on projection on the direction on circumferential direction OU. In the slide it's the horizontal direction. So, and finally we receive two equations. One, it's projection to the axial direction, it's the first one. And the second is the projection to the circumferential projection. So what I want to say to you, these two equations, it's the momentum equation for the compressor. It's really strange, but momentum conservation equation for the compressor contain two equations, contain two projections. The first, second moment, equation. This equation could to help to us to calculate Pu and Pa, the projection of the forces which impact to the blade from the flow. Why these forces are important? Because these forces are used for the stress calculating of the blades, and they are create the lean, they are twist the blade, and it's important to calculate it. It's important to determine the stresses which are produced inside the blade, and using these equations, we are determining the gas forces which act into the blades. That's why these formulas are important. And the last idea, and maybe most important idea from the momentum equation. So I will ask to you one interesting question. But before we will ask, I want to pay your attention at one moment. The blade row are rotating to the right direction. This green arrow show to the direction of the rotating. And flow are moved at the picture from the top to the down of the slide. It's the main direction of the flow movement from the blade roll. So, do you see some strange things at this picture? Do you see some unusual moment at this picture? No? Are you sleepy, guys?
No, I don't see.
You don't see. Okay. Okay. First strange thing. The blades are moving to the right direction. But we have this force which acting to the blades. And this force direct in the direction opposite to the direction of the movement. It's strange. What we are moving blades to the right direction, but we have the force Pu, which create resistance to the movement because it's acting to the opposite direction. It's really strange. So we are moving blades to the right, but we have force which not allows to us to move to the right direction. And this force Pu create resistance. And because we have force which create resistance, we need to supply mechanical energy to overcome this resistance. So, because we have force Pu which create resistance, we need to supply mechanical energy to overcome this resistance. That's why we need to rotate compressor to become it operate, to start operating process of the compressor, because we have force Pu which to us move blades. It's the first moment. The second moment, the second strange thing. Typical task. You have the volume, this is the high pressure. So it's the volume and you have high pressure at the inside. And you have the volume, this is the low pressure. What you are receive if you are connect these two volumes? typically, at this case, we receive what the gas will be moved from the region of the high pressure to the region of the low pressure. It's typically. Yes?
Yes.
Yes. And let's look to other compressor. We have low pressure at the inlet and we have high pressure at the outlet. And flow moves from the region of the low pressure to the region of the high pressure. It's not like at this example. Why? Why the flows in the compressors are moved from the region of the low pressure to the region of high pressure? Because usually they have opposite direction of the flow movement. The answer are very simple. If something are moving, it's mean what some force acting to this flow. That's why we need to find the force which are moving the flow. And we could to find it. This force RA acting from the blades to the flow, and the direction of this flow are the same like the flow direction of the flow of the main flow. So that's why we could to say what the force RA push the flow through the compressor. And that's why finally we could to say what force PU create resistance to the rotation of the wheel. Force RU supply the mechanical work to the flow, and force RA push the working fluid through the blade roll. And the same for the turbine. We are do the same things. We are draw the random line and they are make the same line at the random channel. We are write the momentum conservation equation for this case, and finally we are receive these two equations. These two equations, it's the momentum equation for the turbine. It looks like the equation for the compressor, only one exception. Here sign plus. The first equation the same like for the compressor. And let's analyze the forces and flow movement, rotational movement direction at the turbine. So what we finally have, the direction of rotation of the turbine to the right. And we are looking to the blades and we see what force PU have the same direction like the direction of rotation. And that's why we could to say what force PU, it's the force which are cause of the turbine rotation. So the turbine are rotating because we have force PU, which direction correspond to the direction of the rotation. So that's all about the momentum equation. In reality, it's very interesting equation, and it's really useful because you could use this equation for the calculating of the gas forces which impact to the blades, and you could use it during stress calculation. And this equation explains to us why the turbine rotate, because we have force PU which rotate the blades. And finally, it's this equation, this law, I explained to us why we need supply mechanical energy to the compressor and why the air comes through the compressor from the region of low pressure to the region of the high pressure. So I think that's all about this equation. Do you have any questions?
Yes, about PA. If what is it? It's the R which is going down. It must be higher than PA, no?
So this force are equal to this force because by third law of the Newton. But
Yes.
the point of application are different. This force R A I applied to the flow, and this force R PA are applied to the blades. So this force for the blades, this force for the flow.
Okay. Yes. Okay.
That's why force PA are not influenced to the flow. It's acting to the blade.
Okay. Yes.
Perfect. So some additional questions? No?
I have another question about the methodology for flow paths, but on this.
Perfect. Okay, if you have no questions about the lectures, okay, let's discuss the flow path.
It's just there is a formula which is L divided by Z U average square. L is the specific word of the compressor, but what is
It's hard to. So you mean L divided by U? This one?
use?
And number of stages, yes?
Z is the number of stages?
Yes,
Okay,
Z,
okay.
it's the number of stages because from thermodynamic calculation, you know specific work of all cascades. You don't know the information about one stage from thermodynamic calculation. And we make assumption what we are distribute specific work are uniform between the stages. And that's why you are take the specific work of the cascade from thermodynamic calculation and divide it by number of stage. It's the number of stage. Uh, uh, it's mean what you are receive the averaged value of specific work per one stage.
Okay.
And you are divided it by circumferential velocity, you are receive load coefficient for one stage because Smith chart it's for one stage.
Okay. Thank you.
Perfect. So, okay, guys, I think that's all for today.